How will this universe end? This may be the one prediction of general relativity that we never directly verify, until, well, the very end. Yet the fact that Einstein's theory allows us to learn the answer to this question is incredible. Let's see how this is even possible. Soon after Albert Einstein proposed his general theory of relativity, industrious physicists, and in particular a brilliant Russian named Alexander Friedman, applied the new theory to the whole universe. Combined with observations of the redshifts of galaxies, this showed us that the fabric of space itself is expanding. Recent astronomical observations have revealed something even stranger. The future expansion of the universe will be dominated by a mysterious influence that physicists have come to call dark energy. In order to get a truly meaningful sense of the forces governing the fate of our universe, and especially the nature of dark energy, we're going to have to go pretty deep. We'll need to peer into the mathematics of general relativity. Trust me, it'll be worth it for the amazing insights we'll gain. For today's episode, we're going to start by describing the universe without dark energy, because, well, baby steps, and the answer we get for the fate of our own universe will still be right in one very important aspect. At the heart of general relativity are the Einstein field equations, which look like this. Equations, plural. See, that G and T are what we call tensors, multi-component, multi-dimensional quantities. G is the Einstein tensor, and it defines the shape, the curvature of space-time. T is the stress-energy tensor, and it describes all of the energy, the pressure, the momentum, and more, all of the stuff within that space-time. Both have 10 independent components, giving 10 independent field equations to describe the response of the fabric of the universe to everything it contains. John Archibald Wheeler put it more simply: space-time tells matter how to move, while matter tells space-time how to curve. Now, before we do any general relativity, let's develop intuition a bit by thinking about gravity from a Newtonian perspective, as a force, rather than as an Einsteinian space-time curvature. If I throw an apple in the air, then gravity pulls it back down. The faster I release it, the further it travels before falling back. If I throw it at 11 kilometers per second, which is the escape velocity at Earth's surface, then by the time it almost stops moving, it will be so far away that Earth's gravitational pull will be close to zero. Now, this escape velocity comes right out of Newton's universal law of gravitation, which itself can be derived from the Einstein equations. The mathematical step from Newton's gravity to escape velocity comes from thinking about energy. As the apple rises, its kinetic energy, its energy of motion, is sapped by the gravitational field and converted into potential energy. Remember, energy is always conserved. There's a minimum kinetic energy that the apple needs in order to escape the energy-sucking gravitational potential well of the Earth. That minimum kinetic energy tells you the escape velocity. In this Newtonian analogy, and remember, ignoring dark energy, the universe also has an escape velocity that lets distant galaxies escape each other's gravitational influence. Based on the amount of stuff in the universe, there's some current expansion speed that would allow the future expansion rate of the universe to slowly grind to a halt over infinite time. How do we calculate the escape velocity for the whole universe? By solving the Einstein field equations for the whole universe, of course. It's mind-blowing that we can actually do this, and only possible because on its largest scales, billions of light years, all of the galaxies and galaxy clusters are very evenly dusted across all of space. When we ignore the bumps and wiggles caused by individual galaxies, the resulting smooth universe lets us reduce those 10 Einstein equations to only 2 relationships called the Friedman equations, devised by our boy Alex. The first one can be written like this. That may not look simple, but trust me, we can read this in simple English. That letter A is called the scale factor, and it represents the size of the universe, although it's more accurate to think of it as the average distance between galaxies. Now the Friedman equation tells us how A evolves over time. That's what that A with the dot on top represents, the speed of the expansion of the universe. And for you guys who've taken some calculus, that's the time derivative of A. Let's stick to the left-hand side of the equation for the moment. It reflects the same balance between kinetic and gravitational potential energy that we saw in our rising apple. In fact, this Friedman equation is an energy equation. That first piece, the A dot over A squared, is analogous to the kinetic energy of expansion, how much outflowing oomph the universe has. But that oomph is resisted by the gravitational effect of all the matter and energy in the universe. That's this rho thing, the density, how packed with stuff the universe is. So this second piece represents the capacity of the universe to slow itself down and is analogous to the gravitational potential energy. The balance between these two energy-like terms tells us the fate of the universe. So, what are the possibilities? If the kinetic energy of expansion and the potential energy of collapse are perfectly balanced, then the universe will expand to a ginormous size and grind to a near halt. Essentially, that's if the expansion is exactly equal to the escape velocity. In that case, the left-hand side of the equation adds to zero. But if the left-hand side comes out just a little bit positive, that represents a tiny bit of extra oomph. There will be some expansion energy remaining after gravity is diluted to nothing and the universe will expand forever, never stopping. And if the left-hand side is negative, in that case there was never a high enough expansion rate to reach that extreme size. The universe will eventually fall back inwards and we'll see many of those distant galaxies up very close and personal as the universe undergoes the big crunch. So, what's the answer? Will the universe expand forever or collapse? Well, we know the expansion speed. We measure it from the redshifts of galaxies, as well as other independent methods. The expansion rate now is what we call the Hubble constant. It's around 70 kilometers per second per megaparsec. For a long time, until the late 90s, it was believed that the answer to whether the universe would recollapse lay in measuring rho, the density of the universe. Astronomers worked for decades to weigh up the galaxies across vast swaths of the universe, including their dark matter. But the density of the universe turns out to be too low, only about a quarter of what is needed to reverse the expansion. The density term, the recollapsing term, falls short of the expansion term. The left side of the Friedman equation is positive. There's no way around it. The universe will expand forever. In a way, we're lucky to be living in an era where we can still even see the distant galaxies. Over billions of years, they will slip beyond our cosmic horizon, leaving only darkness beyond the local region of the Milky Way. But wait, we never got to the right side of the equation. We know that it should also be positive because, well, equal sign, but that right side describes something completely different to the left. It describes the shape of the universe, its spatial curvature. According to the first Friedman equation, the fate of the universe, as determined by its expansion and density, should be intrinsically tied to its shape. After all, matter tells space-time how to curve. We'll see in the next episode that there's a surprising mismatch between the left and the right sides of the first Friedman equation that tells us that we're missing something crucial. That something is dark energy. I'll show you why the Friedman equations tell us that dark energy must exist in this universe, and what these equations can tell us about its true nature. Now, don't get your hopes up. Dark energy won't save us from infinite expansion. Quite the opposite, in fact. Dark energy accelerates the expansion, and to understand how it does so will take us far beyond the capacity for Newtonian analogy. It'll shatter our intuitions about energy conservation and gravity on the larger scales of space-time. Hey guys, before we get to comments, a quick shout out. It's Webby time. PBS Digital Studios has been nominated for Best Science and Education Video/Channel. If you guys could head over there and vote, that would be really helpful. link in the description. Okay, so last week we talked about nucleosynthesis. Let's see what you had to say. Enrique Rigatano points out that there seems to be this main sequence of elements produced in the cores of dying high-mass stars, and asks how elements out of this sequence get produced. Okay, that's a great question. In fact, there are many different fusion reactions occurring in the cores of those dying high-mass stars. Some of the most common involve either adding helium, that's helium capture, or losing helium after another fusion reaction. So, if you start with an even atomic number element like carbon with its 6 protons, this means that you end up with a much higher abundance in even-numbered elements than odd-numbered elements. Of the 10 most abundant elements in the universe, only 2 have an odd number of protons, hydrogen and nitrogen. However, there are many ways to build elements out of this sequence in fusion reactions that just aren't quite as productive. As for fluorine, that's actually one of the more confusing ones because it's not produced efficiently in any known reaction in high-mass stars. But recent work has suggested that it might actually be formed in lower-mass stars like our Sun after they enter the red giant phase. There's this brief period when it's possible for material near the core to be carried to the surface by convection and then blown into space as the outer layers are blown away into a planetary nebula. A lot of you are interested to know where the actual elements in our bodies came from and where the supernovae that produce those elements and their remnants are now. So, the disk of the Milky Way, it rotates approximately once every 230 million years or so. However, stars don't all orbit at exactly the same rate. Orbits aren't perfectly circular, and stars drift apart as they move in and out of the spiral arms, and above and below the galactic disk. The Sun has orbited the Milky Way around 18 times since it formed, and so by now it's wandered very far from the giant cloud of gas from which it formed. That cloud is long gone anyway. It collapsed into the Sun's sibling stars, which are also scattered across the galaxy by now. And it was blasted away by supernovae from the most massive stars it produced. The elements that form the Earth and that form you may in part be from those supernovae, but more will be from previous generations of stars that enriched that giant cloud before it formed stars of its own. And last of all, thanks to you, Rod Landata, for sharing this beautiful Serbian proverb. Be humble, for you are made of earth. Be noble, for you are made of stars. Can we try to predict the fate of the universe? Amazingly, yes we can. Yet our efforts to do so have revealed the existence of a strange influence called dark energy. Einstein's general theory of relativity allows us to describe the behavior of the cosmos on the largest scales, of a volume of space vastly beyond our capacity to physically explore, and at a time billions of years in the future, but attempts to constrain the predictions of this theory with real astronomical observations tell us that the fate of the universe is governed by something we call dark energy. To truly understand dark energy, we're glimpsing into the workings of Einstein's theory on a cosmic scale. In the last episode, we looked at how general relativity, expressed in the first of the two Friedmann equations, can describe the cosmic balance between the outward expansion of the universe and the resistance to this expansion due to the gravitational effect of everything it contains. Seriously, you have to pause now and watch this episode if you haven't already. Okay, ready? So, it turns out that this cosmic conflict will be won by expansion. And this is true even though we haven't taken dark energy into account yet. By weighing up all of the matter in the universe, astronomers have figured out that there just isn't enough of anything to turn the universe back on itself. There will be no big crunch, and the universe will expand forever. There are two powerful and completely independent measurements that can test this prediction of the fate of the universe. Today, let's look at one of these measurements, the geometry of the universe, which points to a discrepancy in the first Friedmann equation. We know for sure that the left side of this equation, the sum of the expansion and density terms, don't cancel out to zero. In fact, they come out positive, which means that the expansion term wins over the inward pulling density term. The universe is too low density to recollapse. Right, so the left side of this equation, as we wrote it, is positive, which means the right side should be too. See, equal sign. But that right side actually talks about something completely different. It describes the curvature of space, and it hinges on that K thing. K is in a sense the shape of the universe, its spatial curvature, as well as its spatial extent, finite or infinite. Notice I said spatial curvature. Space-time will be curved no matter what, which is what gives us the expansion described here. But the spatial geometry of the universe at a fixed instant in time can be flat or curved. And it's pretty straightforward. K can be +1, -1, or 0. K equals +1 means the universe has a positive curvature spatial geometry. Spatial snapshots of the cosmos at an instant in time will be curved like the surface of a sphere, except the 3D surface of a 4D hypersphere. In a universe like that, geometry is weird. The angles of triangles add up to more than 180 degrees, and circles and spheres contain more internal area/volume than their circumferences or surfaces should allow. But the total spatial volume of such a universe is finite, and we call that a closed geometry. If K is -1, the universe is the 3D version of a negatively curved hyperbolic plane. Triangles add up to less than 180 degrees, and surfaces hold less volume than in flat space. Such a universe is infinitely large, or open. But K equals 0 means the universe is flat, zero spatial curvature at any given time. Geometry works just as you learned in school, and a flat universe is still infinite, open, in all three spatial dimensions. But check it out. This gives us a way to independently verify what we got on the left side of the first Friedmann equation when we measured the universe's density. The left side has to equal the right, so assuming we got the equation correct, then the shape of the universe should be intrinsically tied to its fate. An overdense, recollapsing universe should have a spherical geometry. An underdense, infinitely expanding universe should be hyperbolic. And only a universe with exactly the right density, that's expanding at exactly its escape velocity, one that will slow to a stop over infinite time, should be flat, with the both left and right sides coming out to 0. Okay, cool. That's something we can test. See, we can measure the shape of the universe, and so measure K, just by checking how geometry works on cosmic scales. Now, if we got everything right so far, the geometry should turn out to be hyperbolic, because that gives us a positive right-hand side to match the positive left-hand side we got from weighing our universe. In fact, we already talked about this in our episode on inflation. Check it out. Observations of the size of the cosmic microwave background features allow us to verify that the longest triangles in the universe have angles that add up to exactly 180 degrees. That's the straight-up geometry of a flat Euclidean universe, flat to within 0.4 of 1%. The right side of the first Friedmann equation has to be very close to 0. This is totally inconsistent with the level of positive curvature we'd expect from an infinitely expanding universe. So, did we mess up our measurements? Is general relativity wrong? No. But when we tried to describe the universe by reducing the Einstein field equations into the Friedmann equations, we missed something. We missed the cosmological constant. We also talk about this in inflation. The very same addition to the Einstein field equations that can describe cosmic inflation can also fix this little problem with the first Friedmann equation and geometry. When we derive the first Friedmann equation with the cosmological constant included, that's the lambda symbol here, we end up with this little extra something on the left. Assuming the cosmological constant is positive, this works on the side of the density term to help bring the left side down to 0, to flatten the universe. So, even though the density is still too low to reverse the expansion, with this new player in the game, geometry is no longer tied to the fate of the universe. A flat k=0 universe can expand forever. But what does this cosmological constant thing actually do? The expression cosmological constant is a clue. This term, as we commonly interpret it, is constant. As the universe expands, regular matter and energy get diluted away. The weird stuff described by the cosmological constant doesn't do that. Its density stays constant. So the bigger the universe, the more of this energy. We call it dark energy, and we interpret it as an energy possessed by empty space itself, by the vacuum. When the universe gets large enough, the density of regular matter will at some point drop below that of this vacuum energy, as described by the cosmological constant term. At that point, dark energy will govern expansion. But when will this happen? Billions of years from now? No, it's already happening. In fact, the universe reached that tipping point pretty recently on cosmic timescales. We now live in a universe dominated by dark energy. How do we know this, and what are the possible consequences? Soon, we'll get to the second and most compelling piece of evidence for dark energy and for the cosmological constant, and along with it, the second Friedmann equation, which will give us the insight we need to understand dark energy's effect on the future of space-time. Some of the topics we've been diving into lately have been pretty high level. If any of you are looking to brush up on your basic physics, or you're looking for some more great physics content, PBS Digital Studios has an awesome new show for you. Crash Course Physics is hosted by Dr. Shini Samara, a mechanical engineer and fluid dynamicist. We've got a link to it in the description, go ahead and check it out. Now, last week we talked about the fate of the universe. Let's see what you had to say. Okay, a number of you were curious to know on what scales of space is the universe really expanding. So the universe is only expanding on the largest scales, not at all inside atoms, inside humans, the Earth, even inside the Milky Way. Within these regions, the shape of space-time is dominated by the gravitational field of the densely packed matter, and expansion is not occurring. In fact, you need to get millions of light years from the Milky Way for the gravitational field of the Milky Way and Andromeda to not dominate the shape of local space-time. Only outside that influence does expansion become significant. Now, there are certain models of dark energy that could have space on smaller scales expand, resulting in the so-called Big Rip. We'll get to that. Michele Goulart would like to know whether the density we use in the Friedmann equation includes dark matter. Absolutely. The density that we calculate when we figured out the fate of the universe does include dark matter, which we can measure by its gravitational effect in several independent ways. Even with dark matter, the universe is just not dense enough to recollapse. Tomek Woof would like to know what the job prospects are for bachelor's or master's graduates in physics. Hey Tomek, great question. So actual research jobs in physics typically require a PhD, but if you have a knack for math and a passion for physics, that shouldn't deter you. However, you can do pretty well with just a bachelor's or master's in industry. Various tech fields have a high demand for bachelor's or master's physicists, like medical imaging or radiology, energy industries, meteorology, science education, science journalism, and definitely information technology of all types. And if you choose, you can always sell your soul for the big bucks in finance, business consulting, patent law, etc. Physics graduates are hot recruits, due to their killer problem-solving skills. And in fact, in 2009, the National Association of Colleges and Employers found that new graduates from physics major programs have starting salaries higher than any other science major. Mr. B is asking for our outtakes of Apple mishaps. Well, I'm sorry, Mr. B, but this is a very serious science education show. We don't stoop to blooper humour. And besides, we get every take right the first time. If I throw it at 11 kilometers per second, is that the good, the up throw there, or should I be really doing something at 11 kilometers per second?
Great, I thought it was good.
And we destroyed the apple.
Action.
Now, before we do any general relativity.
Start again, I had some eyebrow stuff going on.
That was my acting. The idea that the fate of our universe is governed by forces that we can see was abandoned with the discovery of dark matter. However, we now know that the evolution of our universe is driven by something even more mysterious: dark energy. In the last two episodes, we talked about how the fate of the universe can be described using Einstein's general theory of relativity via the Friedmann equations. However, there was a problem. Observations show that our universe is infinitely expanding, but it's also geometrically flat. And this is only allowed if we introduce a new type of energy represented by the cosmological constant. We call it dark energy. But what does this dark energy thing actually do? The answer comes from another piece of evidence of its existence, which itself came from an independent attempt to determine whether the universe would recollapse. See, measuring the density of the universe is one way to determine its fate, because the future expansion rate does depend on density. However, so does its past expansion history. In fact, measuring the past expansion history should tell us the future expansion without ever having to count any galaxies. That history is coded in every photon of light that reaches our telescopes from the distant universe. See, as space expands, it stretches out the light that is travelling through it during that expansion. It increases the wavelength of these electromagnetic waves, resulting in what we see as redshift, cosmological redshift. If we also know how long a given photon was travelling through that expanding universe, then its redshift tells us the total amount of expansion that happened during that time. But how do we figure out how much time the light travelled for? Well, we know the speed of light, so we need to figure out how far it travelled, the actual physical amount of space the photon had to traverse to get to us. To measure the expansion history of the universe, we need to measure the redshift distance relationship. We talk about that in detail in this episode. But wait, doesn't redshift tell us distance? Well, sort of, but only if we assume a redshift distance relationship. Redshift is the amount the universe expanded during a photon's journey, and distance is the amount of physical space it travelled through. And the two are connected by the universe's expansion history. Measuring many different redshifts and distances independently of each other tells us that expansion history. No problem. Just measure redshifts and distances for a bunch of things out there in space. Well, not so fast. Although it's not so hard to measure redshift, distance is one of the hardest things to get in astronomy, especially for things so far away that the universe will have expanded significantly in the time it took their light to reach us. So billions of light years distant. You know what would be really handy? If something else happened to that travelling light that independently kept track of the distance it travelled. Oh wait, there is. Faraway things are fainter than nearby things. We just need some source of light out there whose true intrinsic brightness is known. That way, we can figure out how far away it is just by seeing how faint it looks to us. We call such a magical source of light a standard candle. And we kinda got lucky there. There's a very special type of supernova that's both spectacularly bright and for which we can figure out very accurate intrinsic brightnesses, or luminosities. It's a type 1a or white dwarf supernova. Take a white dwarf, the leftover core of a dead lower mass star like our Sun, and let it cannibalize some of the material from a binary companion. When the star reaches a critical mass, a runaway fusion reaction obliterates the star as a supernova. These things explode with very similar and very high luminosities, so they're the perfect standard candle. Okay, so here's the experiment. Watch stars explode across the cosmos. When you catch a white dwarf supernova, you know its distance and redshift. Hypothetically, if the redshift for a given distance turns out to be on the large side, then that would mean the universe expanded a lot during the corresponding light travel time. Now that actually points to a more dense universe. Why? Because if the redshifts are large, then the universe was expanding much faster in the past, which means something would have had to slow it down to its current rate. That something would be a high mass energy content that could, in the future, cause it to recollapse. So, measuring a rapidly expanding universe in the past points to it having had its gravity brakes on between then and now. On the other hand, if the redshift at a given distance turned out to be on the small side, that would mean that the universe expanded less while that photon was travelling. And so a lower density of matter would be needed to explain how the universe slowed down to the current rate of expansion. The smallest redshifts you'd expect would be if the universe has always been expanding at the rate we see now, so almost no matter slowing the universe down. Such a universe would certainly expand forever. We can also flip this logic and say that for a given redshift, we would expect supernovae to be bright or closer in a high-density recollapsing universe, and faint or more distant in a low-density, infinitely expanding universe. Two separate teams of astronomers spent years catching white dwarf supernovae exploding in galaxies billions of light years away to measure the past expansion history of the universe. They thought this would tell them whether the universe would expand forever or recollapse. But what did they see? In 1998, both teams announced that the universe was expanding even slower in the past than it is now. The redshifts were way too low, or conversely, the supernovae were fainter than you'd expect, even for a universe that has no matter in it at all. That means the expansion rate of the universe has actually sped up, accelerated, while that supernova light was travelling to us. This discovery of the accelerating expansion of the universe earned both teams the Nobel Prize in 2011, and it's considered to be the discovery of dark energy. See, this observation actually came before the discovery of the inexplicable geometric flatness of the universe that we talked about last time. However, this accelerating expansion can be explained with the same bit of math, the cosmological constant, pointing to the same physics, dark energy. Add the cosmological constant to the first Friedmann equation, and we reconcile the left and the right side. But we also see that the constant nature of this term means that the larger the universe, the more of this stuff there is. This lets us interpret the cosmological constant as representing a sort of vacuum energy, a property of space itself, and it must eventually dominate the evolution of the universe. But why should a constant vacuum energy cause the universe to accelerate? Let's take a mathematical ride into the far future, when the galaxies will be so far away that the density of the universe will be basically zero. We know that the universe is flat, so the curvature is also zero. For that far future universe, we can write the first Friedmann equation like this. See, expansion will only depend on the cosmological constant. So does that mean the expansion will become constant? No. See, it's not the expansion rate, the A dot, that's constant in this equation. A dot over A will become a constant. We also call this the Hubble parameter, and it can be thought of as the rate at which the universe doubles in size. The Hubble constant is just the Hubble parameter for the present day. Typically, the Hubble parameter becomes lower over time. but with a positive cosmological constant, the universe will eventually have a constant Hubble parameter, and so we'll have a constant doubling time. That's exponential growth, and it looks like an accelerating expansion. Currently, there's still enough matter in the universe to influence the expansion rate, but we're already at the point where dark energy dominates. In fact, the universe has been accelerating in its expansion for 6 billion years or so. That's what we see in our white dwarf supernova measurements. If the cosmological constant stays constant, we can expect an exponential growth to continue. But will it stay constant? Could it go down, up? That all depends on what this energy of empty space really is. For that, we'll need another episode of Space Time. In the last episode, we talked about how a general relativistic description of the expansion of the universe requires dark energy. You guys had some excellent questions. Pravar Parekh points out that we can't really know that the universe is flat because we can only see a small part of it. This is absolutely true. We can't rule out curvature below our current best sensitivity, which at the moment is 0.4% of perfect flatness. The universe could be positively or negatively curved below that level. If positively curved, that would mean a finite, but very, very large, greater universe, with a volume at least 250 times that of our observable universe. We talk about that in this episode. However, the degree of curvature required by the first Friedmann equation to agree with the balance between expansion and density is much, much greater than our universe exhibits. Even if the greater universe is curved, we still need dark energy. Yeshwanth Viendla would like to know how we can possibly measure the density of such a huge universe. So the handy thing about a universe that's smooth on its larger scales is you don't have to measure the density of the whole thing, just of enough representative patches of it. Our galaxy surveys have worked for decades to measure brightnesses, redshifts, stellar compositions, and more of many millions of galaxies, and even then they don't cover the entire observable universe. However, they do sample a large enough fraction of it to tell us that matter in the universe is pretty smoothly distributed. These surveys don't measure dark matter content of all of their galaxy clusters, but again, we've weighed up the dark matter in enough of them to be able to extrapolate. Thomas Waclav has a reasonable concern about just adding stuff to your math until it works. Thomas, I hear ya. You can't just do that. William of Ockham turns in his grave. But when the theory, general relativity in this case, is so thoroughly verified in so many other ways, and the addition of the cosmological constant works so well to describe the discrepancy, it strongly suggests that this addition describes something real. As we saw today, the cosmological constant solves two major discrepancies, so at some level it's right, even if we don't know what causes it or whether it's truly constant. Austin Pinheiro likes to think that PBS stands for peanut butter sandwich for no apparent reason. Don't sweat it, Austin. People think silly things all the time. Thanks to you for being honest about the strength of the evidence behind your belief structure. In the past few episodes, we've delved deep into cosmology, building up the tools we need to really understand dark energy and its influence on the universe. Pretty soon, you'll understand as much as anyone, with the possible exception of people who are actually paid to understand dark energy. But before we get there, it's time for some homework. Today, I have a challenge question for you. First, if you haven't watched these 3 episodes, you'll want to do that. We live in unusual times. The balance between dark energy and matter in the modern universe is on the side of dark energy. The expansion of the universe has been accelerating for some billions of years now, ever since it became large enough for regular matter to dilute away enough so that dark energy dominates. But we're still very near that tipping point, so close in fact, that it feels like a huge cosmic coincidence. This genuinely puzzles many cosmologists. If you add up the energy in any large volume of space, about 70% of it is dark energy, and the remaining 30% is in the form of regular matter. And by regular, I also mean dark matter, which is actually most of that 30%. Now, these percentages aren't for some abstract quantity or influence. I'm talking about the relative amount of energy. So the number of joules, ergs, British thermal units, energon cubes of this stuff in a large volume, say a cubic million light years. Around 70% dark energy, 30% matter. So there's more dark energy than the other stuff. But there's something really weird here. These numbers are extremely close to each other. I hear you ask, how are 70% and 30% close to each other? I mean, 70% cacao dark chocolate is very different and much tastier than 30% milk chocolate, right? Thanks for asking, and I agree about dark chocolate. But if our universe were chocolate, which it isn't sadly, then it's only been deliciously dark for a relatively short period. Let me explain. In the Einstein field equations and in the Friedmann equations that are derived from those, dark energy is described by a positive cosmological constant. If that constant truly stays constant over time, then it represents an energy of the vacuum. Its density stays constant, and so the amount of dark energy increases at the same rate as the volume of the universe. When the universe is doubled in size, there'll be twice as much dark energy, joule for joule. And when it was half its current volume, there was half as much. At the same time, the total amount of regular matter in any expanding region remains constant. That means the density of matter decreases as the universe expands. At some point in the past, there was a perfect balance between dark energy and matter. How long ago? Very roughly, it was when the universe was half its current volume, because that would mean half the current amount of dark energy. A given giant box in the universe currently has around 30 parts matter and around 70 parts dark energy. Half its volume, and it still has those 30 parts matter, but only around 35 parts dark energy. Close enough to 50-50 for an astronomer. How long ago was that? Well, the volume of that giant box is equal to its linear size to the power of 3. We can think of that linear size as the scale factor of the universe. So the scale factor, the size of the universe, only needed to be around 20% smaller than it is currently for the volume of any patch of space to be smaller by half. Assuming a constant expansion rate, a constant increase in the scale factor, that means it was only 2 to 3 billion years ago. Blink of an eye, really. No, really. Dark energy has dominated the universe only during the tenure of life on Earth, although its effect has been felt for a bit longer than that. Think about it this way. Since the end of the inflationary epoch, when the universe was about 10 to the power of minus 32 seconds old, and around the size of a grain of sand, it has doubled in size approximately 100 times to get to its current size. That's 100 doublings of its scale factor, so its linear dimension, not its volume. It'll go on to double in size approximately infinity times in the future. Okay, so let's think about time, not in billions of years, but in the number of doublings. For the vast majority of those past 100 doublings, dark energy has had an extremely tiny energy contribution. Seriously, practically zero. And for the vast majority of future doublings, regular matter will have diluted away and be an infinitesimal influence compared to dark energy. It's only right now that both have a measurable effect. Here's your challenge question. For how many of those past 100 doublings has dark energy had any significant effects? Let's say at least 10% of the energy density. And for how many of those infinite future doublings will regular matter and energy have any significant effect? Again, at least 10% of the energy density. And the extra credit question. Answer the question I just asked, but also tell me how many billion years ago dark energy started to have a significant effect, and how many billion years in the future will it take for matter to cease to matter? For the extra credit part, you can make some crude approximations to get a rough idea with only simple algebra. Or you could go ahead and solve the Friedman equations. Up to you. I'll choose 3 correct answers at random for both the main and the extra credit questions to receive SpaceTime t-shirts. To be eligible, you need to explain your reasoning and show your work. Feel free to propose any solutions you come up with for this apparent cosmological coincidence. You also need to not give answers in the comment section. That will disqualify you from this and future challenge questions. Email your answers to pbsspacetime@gmail.com with the subject line, Dark Energy Challenge, within 2 weeks. We filter by subject line, so make sure you use exactly this phrase to be considered. See you next week for a fresh new episode of SpaceTime. This episode is supported by the Great Courses Plus. Did all of dark energy just vanish? A team of scientists have analysed new data and claim that we need to completely rethink its existence. Back in 1998, 2 independent teams of astronomers made an extremely controversial announcement that the universe is not only expanding, but that expansion is accelerating. They discovered this by watching for the explosions of Type 1a supernovae. These exploding white dwarf stars have predictable brightnesses that allow astronomers to figure out how far away they are. With a set of reliable distances extending back several billion years, the teams were able to map the expansion history of the universe. They expected to see that this expansion rate was slowing down due to the gravitational effect of all of the matter in the universe. Instead, they found the expansion rate has been accelerating for half of the age of the universe. It appeared that something was acting to counter gravity, an outward pressure that has come to be known as dark energy. The finding led to a shared Nobel Prize for the leaders of the supernova hunter teams, Adam Rees, Brian Schmidt, and Saul Perlmutter. For a deep dive into the mysteries of dark energy, we actually already made this entire playlist on the topic. It's pretty hardcore, so definitely check it out, but maybe after this video. So why are we talking about dark energy again? Because another team has just announced a new analysis of updated supernova data. They claim the data are consistent with there being no dark energy, no accelerating expansion. They suggest the universe may be just expanding at a constant rate, never speeding up, but also not slowing down. This claim is just as controversial as the original discovery of dark energy, because dark energy is now the industry standard. Of course, the media jumped all over this and provided almost no useful info. We thought it would be a good idea to figure out whether we should throw away nearly 20 years of work on dark energy and delete our playlist based on this result. In October 2016, the team of Nielsen, Gufanti, and Sakar published a paper titled Marginal Evidence for Cosmic Acceleration from Type 1a Supernovae. It appeared in the prestigious Nature journal, and that helped to get a lot of attention. As with the initial discovery of dark energy, these scientists used Type 1a supernovae to track the expansion history of the universe. However, in the 18 years since the first studies, we've observed a lot more of these exploding white dwarfs, 740 of them compared to the 10 used by Rees and Schmidt and the 49 by Perlmutter. The new guys claim that the much larger sample is consistent with there being no acceleration, and more data equals more confidence, right? So did dark energy just go away? Actually, not at all. And here's why. The new study actually agrees with the old dark energy result. Mostly. It finds that an accelerating universe containing dark energy still fits the data best. The difference is that it finds that the data is also consistent with a wider range of possible expansion histories. And that range now includes a history in which there never was any acceleration. An accelerating expansion is still preferred, it's just that a non-accelerating history is not excluded with quite the same confidence. I want to talk about how scientists analyse astrophysical data like this. So let's talk numbers. The new study claims a 3 sigma confidence that there is a positive cosmological constant. So quick aside, the cosmological constant, written as lambda, is the thing you add to Einstein's equations of general relativity to give the anti-gravitational effect of dark energy. If the cosmological constant exists and is larger than 0, then dark energy is a real thing. Okay, so 3 sigma confidence in a positive cosmological constant basically means this. If you repeated this experiment many times, about 0.27% of the time, the uncertainties, so the messiness in the data, would cause a universe with no dark energy to just happen to look like one with dark energy. So on average, about 1 in 300 experiments gives you a false 3 sigma result. But given that many thousands of different experiments are being run by professional scientists at any one time, false 3 sigma results do happen. So for a really big scientific claim, like the existence of dark energy, 3 sigma just doesn't cut it. Scientists like to get at least 5 sigma significance. False positive 5 sigma results only happen once per 3.5 million experiments. So the new result doesn't give a high enough significance from the supernova data alone. No one could claim a proof based on that. It's at best a very strong hint. But here's something the press skipped. The original papers by our Nobel laureates also claimed a significance of 3 sigma or lower for a positive cosmological constant based on that early supernova data alone. So why did anyone pay any attention? Because they didn't consider the supernova data alone, and nor should we. If we include other stuff about the universe, our confidence in the existence of dark energy rockets well above 5 sigma for all of these studies. We can't yet observe dark energy directly. We can only infer its existence based on how it affects the expansion of the universe. But that means we have to consider all of the things affecting that expansion when we decide whether dark energy is part of that equation. In fact, there are only 2 factors that can change the way our universe expands. There are things that tend to accelerate expansion, which we call dark energy, and there are things that slow expansion, which is just the gravitational effect of regular energy, and that's mostly dark matter, but also stars, planets, gas, radiation, etc. This graph is how we like to show the balance of these energy types. Dark energy on the y-axis and normal energy, so matter, on the x. To be a bit more precise, these numbers, omega lambda and omega m, represent the fraction of the total energy in the universe that these 2 types would comprise, assuming that the universe is flat, which it probably is, and I'll get back to that. Those blue ovals represent the ranges of combinations of matter and dark energy that are consistent with the new supernova measurements. Now, statistical hypothesis testing is a whole big topic, and I'll put some links in the description, but very crudely, the inner circle is the most likely region. That's the 95% confidence, 1 sigma region. But really, omega lambda and omega m could be anywhere in here, although the further from the center, the less likely. The big controversy here is that the 3 sigma contour touches the 0 omega lambda line. So if we consider the supernova data by itself, represented by these contours, there appears to be a small chance that we lie on this part of the graph, little or no dark energy. Except that bottom left corner of the graph also represents a universe that has almost no matter in it either. 0 omega lambda, but also 0 omega m. But our universe definitely has matter in it. We even have a pretty good idea how much. Counting galaxies and weighing dark matter tells us that omega m is probably around 0.3, but it's at least around 0.2. That means we can rule out this entire section of the graph. That alone rules out the region of the supernova results that suggest there's no dark energy. Now this was known in the late 90s, which is why the first supernova results were taken seriously. Another really powerful piece of evidence is that the balance of omega lambda and omega m define the geometry of the universe. If these add together to equal 1, then the universe is flat. And by that I mean that parallel lines stay parallel and the angles of triangles add up to 180 degrees and all the regular rules of geometry work. In a relatively empty, expanding universe, as is represented by this part of the graph, space would not be flat. It would have a weird hyperbolic curvature. I'm going to have to refer you to another vid for details on universe geometries, but the main point is that we can also figure out where we should be on this graph by measuring the geometry of this universe. And as I also talk about in that episode, we can do this using the patterns in the cosmic microwave background to measure the angles of universe-sized triangles. Their geometry appears to be very flat, so our universe should lie on this line here. In fact, I oversimplified slightly, but the CMB results place our universe somewhere in these orange regions, the 1, 2, and 3 sigma contours based on the CMB measurements. That little region where the supernova and CMB results overlap represents the most likely combination of dark energy and matter. When you mathematically combine the certainty contours of two completely independent measurements, they give you a much tighter range of possibilities. And the no dark energy region down there is so far from the combined likely region that we can rule it out with much more confidence than even 5 sigma. And there's other evidence leading us away from that little corner also, like baryon acoustic oscillations, but I'm going to have to leave that one to our previous episodes also. But to wrap up, everything we know about the way gravity works, combined with the expansion history that we measure, tells us that there has to be something out there countering the gravitational effect of matter and flattening the geometry of space. It's not even like accelerating expansion is that weird anymore. We're pretty sure it happened even more quickly in a separate episode soon after the Big Bang in the event we call cosmic inflation. So this is a thing that seems to happen in our universe. Dark energy, whatever it is still a thing. But this new study is still very important. It demonstrates one of the greatest qualities of the scientific process and culture. No matter how well accepted a result is, everything we think we know is always subject to being questioned and retested. We now need to understand why the new result edged the confidence down. There were differences between the experiments, so what effect did these differences have? You can be sure that many scientists will be taking a long, careful look at the evidence for dark energy and its effect on the expansion of space-time. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a digital learning service that allows you to learn about a range of topics from Ivy League professors and other educators from around the world. Go to thegreatcoursesplus.com/spacetime and get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, or become a photographer. New subjects, lectures, and professors are added every month. So Kevin Stacen's course, The Life and Death of Stars, gave me some great insights into the nature of the weird corpses left after stars die. With the Great Courses Plus, you can watch as many different lectures as you want, anytime, anywhere, without tests or exams. Help support the series and start your 1-month trial by clicking the link in the description or going to thegreatcoursesplus.com/spacetime. It's been a few weeks since we did comment responses, so I have some catching up to do. I want to respond to some of your thoughts on both colonizing Mars, as well as on the many worlds interpretation of quantum mechanics. Mars first. Some of you criticized my centrifuge city idea as being a bit overkill, that maybe 0.4G would be just fine for bone health, or at any rate we could just wear heavier clothes. Sure, maybe a centrifuge city is extravagantly awesome. Anyway, walking around in moon boots and lead bodysuits for your entire life is both unstylish and it only helps bones and muscles, it's not clear how organs respond to low G, especially the heart, and especially over many decades. My point is that there are plausible options, and a giant rotating maglev ring city in a sealed torus is actually plausible. Besides, when the rebellion starts, the centrifuge cities will be an important touchstone in the conflict between Earthers and the 0.4 G for true Martians crowds. Okay, on to many worlds. A few of you asked how the double slit experiment is actually performed. Do the slits need to be really tiny? How far apart are they? Etc. Well, the cool thing about the double slit experiment is that it's really easy to do with light. You get the best separation between interference bands when the distance between the slits is similar to the wavelength of the light, and with slit widths significantly narrower than that separation. So that's 500 nanometers separation for visible light. This still works, however, for much larger separations and wider slits. Remember, this was first performed by Thomas Young in 1803 by punching a pair of holes in a screen. In fact, you can see diffraction patterns with your own eyes. You don't need two slits. A single slit also produces dark bands of destructive interference. Make a narrow gap with your fingers and put them really close to your eye and look at a light. You'll see dark vertical lines. Those are fringes of destructive interference, just like the double slit experiment. It's an example of Fraunhofer diffraction. In fact, it even works if you place a single finger close to your eye. The true nature of dark energy confounds even the world's smartest astrophysicists. Its strange anti-gravity effect is unlike anything we've ever encountered. Today, we get to the bottom of it. A few episodes ago, I asked you to take a wild ride with me into the heart of Einstein's general theory of relativity and its description of the vaster scales of our universe. Today, we get the huge payoff for our efforts. We already have some pretty awesome insights. 1. The universe is expanding, and it will expand forever. There's just too little matter in it to recollapse. 2. Such an underdense universe should be geometrically weird, a negatively curved hyperbolic hyperplane. Paradoxically, our measurements point to near-perfect flatness. This is only possible if we missed some unknown type of energy pervading all of space. And 3. The expansion of the universe is accelerating. We know this because we've mapped its past expansion history using distant supernovae. There's an unseen influence at work. We call it dark energy. This dark energy is described by the cosmological constant in the equations of general relativity. It both flattens the universe and leads to exponential expansion. But this is incredible. It means we have dark energy's number, its fingerprints at the crime scene. Knowing a possible theoretical form for dark energy will unlock many of its mysteries. Today, we're going to talk about the simplest interpretation of dark energy, one where the cosmological constant really is constant. It doesn't change over time. All of our data is completely consistent with that being true. A constant cosmological constant represents a non-zero energy of empty space, a vacuum energy. The more space you have, the more dark energy you have. It's a constant energy density. Okay, the big weird fact about a constant vacuum energy density is that it leads to exponential expansion. We saw that general relativity demands this when we looked at the first Friedmann equation. But what physical thing about dark energy is producing this outward push, this anti-gravity? That's what we're going to answer today. Now, the Friedmann equation that we've been playing with so far just isn't going to cut it. It only tells us that dark energy produces an exponential change in the size of the universe, not necessarily an exponential growth. Looking at that equation by itself, it could just as well be an exponential shrinking. To see why dark energy pushes outwards and accelerates the expansion, we need to go deeper. its anti-gravitational effect emerges in the second Friedmann equation. The first Friedmann equation is all about the rate of expansion of the universe. The second is actually much simpler. It's about the acceleration or deceleration of that expansion. It describes the forces pushing or pulling on the expansion. Here it is. Once again, we can read this in simple English. A is the scale factor, sort of like the size of the universe. And A double dot is the rate at which the expansion is changing. It's the acceleration of the scale factor. It depends on the density here, rho. The more matter and energy in the universe, the harder gravity pulls inwards, trying to stop the expansion or speed up the collapse. That's this negative sign here. Positive acceleration outwards, negative inwards. This thing is in a real way just Newton's law of gravitation for the whole cosmos. Okay, so if rho is density, what's this P? That's the pressure due to fast-moving particles and radiation. In general relativity, energy/mass and pressure both curve space-time. The way pressure does this is pretty weird. Think about a pressurized tank. The internal gas pushes outwards as fast-moving particles collide with the walls. So if fast-moving particles produce an outward-pushing pressure, then is this how dark energy is causing expansion to accelerate? By causing positive pressure? No, that can't be it, because pressure only produces a direct force if there's a difference in pressure between two regions, a pressure gradient. In order for the pressure of fast-moving particles to create an outward push, the region beyond them has to be an area of lower pressure. But on the larger scales, the universe is pretty smooth. It's homogeneous, and so the pressure is the same everywhere. Instead, the overall effect of pressure on the curvature of space-time is a purely relativistic effect. See, high pressure from regular matter and energy means very fast-moving particles, and the motion of these particles results in a combination of relativistic corrections. The ultimate effect is that the mass of a region of the universe is higher if its particles are moving quickly, compared to a region where the particles are moving more slowly, even if the overall energy density of those regions is the same. Positive pressure pulls the universe inwards. So it looks like as long as there's anything in the universe whatsoever, that whole right side is negative. So acceleration will always be inwards. In other words, gravity is always attractive. What goes up must come down. Described this way, the universe is never static. It's either expanding and slowing down, or contracting and speeding up. This was actually Einstein's motivation for adding the cosmological constant in the first place. He wanted a static universe, so he added something to his field equations that would give a positive outward acceleration in the second Friedmann equation. Here's what it looks like. The plus sign here can counter the minus sign here. The cosmological constant was designed to work in the opposite direction to regular matter and energy. That's what anti-gravity looks like, mathematically. This is not just some math trick. Dark energy is real physical stuff. And that means its anti-gravity effect must come from its physical properties. The effect of the cosmological constant is the combined effect of dark energy's own density and pressure. So let's describe it that way. In our far future universe, regular matter will have diluted away and will only have the density and pressure due to dark energy, rho lambda and p lambda. Now, the energy density of dark energy is positive, just like regular matter. It has to be, because dark energy helps regular matter flatten the geometry of the universe. That means its density term also works on the side of matter to try to slow down the universe in the regular attractive gravity way. So dark energy's density isn't causing expansion to accelerate by itself. That leaves us with pressure. But we just discussed how positive pressure can't cause expansion to accelerate outwards. It turns out that dark energy does produce an enormous pressure. But that pressure isn't positive, it's negative. A negative P here cancels this minus sign and can result in outward acceleration. That's where dark energy's crazy anti-gravity effect comes from. It's negative pressure. What does negative pressure even mean? Well, positive pressure pushes outwards, like in our pressurized tank. So negative pressure would pull inwards. It would be like attaching stretched elastic bands between the inside walls of the tank. It's a tension. Both have positive energy density, but positive pressure pushes out, negative pressure pulls in. And we're back to that contradiction. Weirdly, the inward pulling pressure of dark energy ultimately drives expansion outwards. Again, this is due to its relativistic effect. The direct effect of dark energy's negative pressure doesn't do anything, because that negative pressure is the same everywhere in the universe. But even though the negative pressure has no direct effect, it has its relativistic effect. Relativistically, negative pressure has to do the opposite of positive pressure and results in anti-gravity. Because math. And the relativistic effect of negative pressure is actually really hard to describe intuitively. And in fact, such an explanation may not be possible. Part of the problem is that negative pressure doesn't come from the motion of dark energy particles, whatever they might be. Instead, it comes directly from the fact that the density of dark energy is constant. Let's say I'm holding a volume of the universe that has a constant energy density. If I expand it, then it has more energy in it than it did before because it has more volume. I would have to provide that energy, which means I'd have to do work to expand it. That's exactly how we define negative pressure. A volume has negative pressure if it takes work to expand, just like a volume with positive pressure takes work to compress. Negative pressure means energy is gained on expansion. That's what happens with dark energy. As the universe expands, more dark energy is created because its energy density has to stay constant. That looks like negative pressure. And yet, this abstract sounding negative pressure has a very real physical effect. It's the opposite effect to positive pressure, and it's a clear outward pushing anti-gravity effect when we look at its role in the second Friedmann equation. In the first Friedmann equation, we see it as an exponential change in the scale factor, but both agree that a constant energy density and the resulting negative pressure leads to accelerating expansion. Okay, so it takes work to expand a volume of the universe, and the energy turns into new dark energy. But who's doing that work? Where does the energy come from? The answer is maybe nowhere. Here's where intuition goes completely out the window. See, the law of conservation of energy no longer applies in an expanding universe. This law is a property of a Newtonian universe in which space and time are fixed, static dimensions. In a universe governed by general relativity, this is no longer true. Energy can be forever lost or gained from nothing within an expanding, curved space-time. In a recent episode, we talked about the Breakthrough Starshot program, Light Sail to the Stars. Let's see what you had to say. So, a few people were wondering how that probe sends its signal back to Earth. Well, the idea is to beam the data back with low-power lasers, or perhaps alternatively, to use the sail itself as an antenna for radio transmission. The signal will be weak, but we'll know exactly where to look and can use gigantic detectors here on Earth. If the signal is sent by laser, then the same phased array that projects the launch laser will also be able to spot the returning laser signal. Patrick Romo and others asked whether we could decelerate the light sail in the wind from the destination star. Well, there's actually no way to decelerate the craft. The impulse generated by the laser is many orders of magnitude greater than that of the star at the other end. No, the craft will zip through the AlphaSend system in a few minutes, recording data as it goes. And this is why you want to send a large number of craft. A few of you suggested that Moore's law is near its end. So while it's true that there's a limit to the miniaturization of silicon chips, Moore's law for computing has been roughly consistent since around 1900, with the first mechanical tabulators, followed by solid-state relay calculators, then vacuum tube computers. If we never move beyond silicon, then maybe we have a problem. But there are already multiple possibilities there. The analogies to Moore's law for laser power, material science, battery tech, etc. are also alive and well. Aging Reversed would like to spend the entire Starshot budget to cure cancer, rather than sending a speck of dust into nothing. Well, the final cost of Starshot is expected to be several billion, but that's similar to the annual budget of the National Cancer Institute and a small fraction of global spending on oncology research. If it were possible to cure cancer with that amount of money, well then we would have cured it in a year. Advances in medical research may produce more tangible benefits, but it's easy to underestimate the benefits of inspiring forward-looking projects like Starshot. They give us a sense of unity and optimism that feeds back into all of our efforts. Inspire enough smart kids to become scientists instead of bankers, and it is well worth it.